This is a web application that I wrote to calculate what I like to call the Khan equation. Sal Khan is the founder of the Khan Academy. And it's an online resource that you can go to take lessons for free. It's a very good resource and I recommend it to you. The Khan equation is different from the Drake equation in that it starts with the number of stars in the Milky Way galaxy, and at the end it takes the longevity of that civilization and divides that by the average main sequence lifespan of the detectable civilization's host star. You can actually see the Khan equation in action. Just search for detectable civilizations in our galaxy on YouTube. Let's take a stab at the Khan equation. In the YouTube videos by Khan, he puts the fraction of stars with planetary systems at a low number 1/4, 0.25. The fraction of those planets with an environment suitable for life, he puts at 0.1, 1 in 10. The fraction of those planets on which life actually appears, he puts at 0.5. The fraction of those life-bearing planets on which intelligent life emerges, again he puts 0.1, 1 in 10. And the fraction of those planets on which intelligent life emerges and develops a technology that releases detectable signs of their existence into space, he also puts at 1 in 10, 0.1. And the length of time in years such civilizations release detectable signals into space, Khan puts 10,000 years. And we're going to divide 10,000 by 10 billion, the average main sequence lifespan of stars. This is sort of misleading because G stars have an average main sequence lifespan of 10 billion years, such as our Sun. Other stars may last longer. In fact, other stars definitely do last longer. K-type stars can last on the main sequence for 60 billion years. M-type stars can last on the main sequence for over 100 billion years. That's older than the age of our galaxy. So let's see what we get for the calculation, and of course it shows up just the way it did on the Khan videos. 12.5 civilizations in the Milky Way galaxy that are detectable. And the average distance to the nearest communicating civilization would be 3,681 light years. Let's go back and change some of the values in the Khan equation and see if we can narrow that down. Now, the fraction of stars with planetary systems we know from Kepler data to be greater than 1/4. It's approaching 1, so it's more like 0.99. And the fraction of those planets with an environment suitable for life is more like 1 in 5, 0.22. The fraction of those planets on which life actually appears, we'll make that 0.5. And the fraction of life-bearing planets on which intelligent life emerges, we'll make that again 0.1. And the fraction of those planets that are able to release detectable signs of their existence into space, let's make that half. And we'll keep this longevity the same, 10,000 years, and click Estimate for N, and we get a different value for N, 544.5 civilizations in the Milky Way galaxy releasing electromagnetic emissions into space. And the average distance now becomes 1,059 light years to the nearest communicating civilization. We can go down and see some very interesting candidate stars. There's a lot of them. Here's one, Kepler 62, which is 1,200 light years away. Kepler 62 is a K2V star. That means it's a K-type star. It's one of the hotter K-type stars, and V means it's still on the main sequence. And we can click on more information for Kepler 62 and look at the planet Kepler 62f. And it's a planet that is larger than Earth, 62F is here, and here's the Earth. So it looks like it's 1.5 times the size of Earth. Could be a water world, could be a rocky world, could be an ice planet, we don't know. The age of the star is 7 billion years, and it's an M-type, or K-type star rather. So that would be plenty of time for life to evolve and intelligence to evolve. And of course, because K-type stars last on the main sequence for around 60 billion years, there's plenty of time for life and intelligence to develop. This image was taken from NASA's Eyes on Exoplanets. Here's the URL for that. It's a very good program. I recommend that you download this program. Here's Kepler 62F. It's a nice circular orbit. And there's another planet in the habitable zone, Kepler 62e, with a nice circular orbit. And all of these planets interior to the habitable zone are also in nice circular orbits, but they're probably too hot for life to develop. We don't know. Maybe. I don't know. So if we go back to this information, since the distance to this star is 1,200 light years, it will take another 1,136 years for any civilization orbiting Kepler 62 to receive our early transmissions. And at that distance, if they are in the mood for conversation and they want to reply back to us, it will take at least 2,336 years to receive a reply. And that is the Kahn equation. Be sure to subscribe to the Floreshime channel. Thank you very much.